Dr. Eric Sortomme, we have Robert Stoddard, and then Tom Gage. Each of these are going to talk about or are currently in the business of electrification and the grid and how the two interact and how there are some potential synergies between those two, not just consuming electricity off the grid, but using electric vehicles to assist with some of those things as well. We only have a half hour. There's 3 presenters, so I'm going to get it out of the way and pass it off to Eric here.
Thank you. Does this thing work?
Yes.
It does. Awesome. Okay, so quick, I'm Dr. Eric V. Sortomme. Yeah, so I didn't have at the beginning the foresight to call myself Dr. EVs, even though when I made my handle, so I'm Rolo's Revenge. If you want a Rolo, come up to me afterwards. My talk is on, EVs in the grid, or when should I charge? So first we're going to talk about sort of an overview on how the traditional power grid works. We've got generation, could be in this case wind, more likely it's big old coal plants or natural gas plants or nuclear plants. There's a transmission system where all our big transmission towers move that energy from the generation plants through substations to the distribution substation right here, and then down your poles that you see, your primary distribution to your secondary distribution through the pole mount transformers to your house. That's the distribution system, and that's sort of how the power grid works. It's generated, it's transmitted, it's distributed, and you use it. Why does that matter? Well, let's look at how generation happens. So every day there's a load curve. There's, people use energy at different times for different reasons. And in general, it's sort of very low at night and gets higher up during the day. There might be a little dip for some reason or another. And then it comes back and repeats the cycle pretty much. In that, they have broken it into 3 different types of load. The part that it never goes below is your base load, and your base load is met by large plants that have very low operating costs, such as this nuclear plant here. It could be coal nuclear, or in the Pacific Northwest, it's hydro. It's all hydro for us. But then your intermediate stuff, it can move a little bit faster. The base load doesn't like to move outputs at all. Your intermediate stuff is natural gas plants, combined cycle, or hydro. And then your peak stuff is very small plants that are cheap to build because they don't run very often, but they're very expensive when they run, and these are often the dirtiest plants. Combustion turbines, or even sometimes reciprocating engines, big old diesel generators that just have to meet this load. How does this change when you put renewables on? When you look at that, you say, maybe I should charge at night because there's not very much load. But renewables have been changing things. So rooftop PV has been making suddenly the middle of the day the part that's actually the lowest load. This is actual graph from Hawaii, where you went from 2010, 2011, 2012, 2013 to the red line 2014, where now the middle of the day is the lowest point, and then as the sun sets it shoots way up, where in the nighttime suddenly you have higher load. And California, they're at this point right now, and they're projecting, because of rooftop PV, it's going to be in the same direction. So the question is, when should you charge then if you have an electric car? Actually, the best time would be during the middle of the day, because that's when the grid can handle it better. What if you're in a place with wind profiles? Well, here's some historic data from the Pacific Northwest, where here's the wind paired against the load. The difference would be the net. You see that the wind is extremely high at night and there's almost no load. So in this case, you would want to charge at night. Let's talk about the distribution system. Transmission system really doesn't have a lot of issues with EVs. So you have your primary distribution, your problems that could happen from EVs charging too much could be a line overload or a voltage sag. With your secondary distribution, your pole top transformers can get overloaded, or the service connect to your house could also get overloaded. that results in these fun things of transformers blowing up and lighting on fire. And some TMC members, I don't know if they're in the audience, have actually reported on this happening both during the daytime when they plugged in and charged at EV gatherings to lose a transformer, or at night where, I can't remember his name, where the service transformer or the service line actually caught on fire and burned down in the middle of the night. So when exactly is the best time to charge your car for the distribution grid? And really the answer is there isn't a set time to best time to charge your car. It depends on all of those different things of the generation state and the distribution state. And so what you would need is some sort of controllable service, a charge valet, where a vehicle-to-grid aggregator, not taking any power from your car, but just monitoring all of the EVs across the grid, as well as the grid states, would look to see that your car is charged in a way that is the way you want it, either charge you for the lowest CO2, or the lowest price, or maybe the friendliest to the grid, make sure that you always have the charge you need to go somewhere, and then you can do so in a way that's optimal for whatever you like. And then this could also give you then like periodic reports to say, by changing your charging schedule from just charging it when you plugged in, you managed to save this much money, or help the utility, like however you help the utility, or save this much CO2, whereas you'd otherwise do it. And so that's sort of one of the areas that's being looked at to help manage this.
Thanks. Well, I am not an engineer. I'm an economist, and I've had over the past 25 years a chance to work on writing the rules of the road for how wholesale power markets work in the United States, which has been a great challenge, figuring out how the money flows need to match the power flows. And how well we do that really depends on, gives the right incentives for people to do the right things. But you screw it up and you get the wrong price signals, you get the wrong behaviors. I think one of the challenges we'll see as we talk through, and I'm sure Tom will hit as well, is if we don't have pricing effects give you the incentive to be charging at the quote right time, or to be offering your vehicle, we're not going to get the right behaviors. I actually stepped down from my position at Charles River Associates, where I used to head the energy practice, to run the commercial side of a new renewable energy company. Let me just briefly show you this. How many here recognize this power plant here? Yeah. Well, it retired in February, in part because I've been working with the owner of the plant, Dynegy, to build a replacement plant for it, which will be using my company's technology. We'll have a wave farm about 8 miles offshore, and it'll generate as much power as this old power plant used to generate, completely without fossil fuels. So that moves along. Obviously, there's a huge lot of regulatory regime between here and there, but we're working. So, I mean, everyone talks about renewables as great things, and in lots of ways they are. Obviously, I've shifted my career towards that. There's no emissions. There's price certainty. That's a big deal. I mean, I'm talking to one of my clients might be an oil refiner. How strange is that? The oil refinery buying renewable power. Well, they know the price. They know for 25 years what the price will be. This lets them make investment in new business, new capital, new employment based on clear pricing. And that pricing doesn't depend on some war in Afghanistan or disruptions in shipping in the Mediterranean. That's all great. But you talk to the guys who run the power grids, and they've got a whole bunch of things they worry about with renewables. They don't really get to tell renewables what level to operate at. The sun is shining or it's not. Some of them they can turn down, like you can, modern wind farms, you can feather the blades so you're producing less power than maximum. But you can't go above the maximum. Output is uncertain, not only day to day, you have a sunny day or a cloudy day, a windy day, not windy day, but even minute to minute, even second to second. And given how a grid has to operate where instantaneously, the amount of power being generated has to match the amount of power being used or lost through transmission losses. This is a really hard problem, adding variable resources onto the system. Finally, we've got a problem of very high capital costs for renewables. That's a talk for a different day. When I talk about the issue of, let me go back up, hopefully. There we go. About minute to minute. So this is a simulation from the National Renewable Energy Laboratories of 15 turbines or 200 turbines, different sizes, slightly different wind conditions. This is over an 8-hour period. And you can see, what looks, you might think about as a smooth curve, but actually a huge amount of detail about how much power is coming out of the grid. All those fluctuations have to be balanced by some counter fluctuation, either in load or some other generation source, in order for that resource to be integrated on the grid. That's a tough problem. Well, day to day or hour to hour, we've got a similar problem. This is a graph from the California Independent System Operator of different wind output across the state on a series of different days. And while the average is pretty constant, you can see that one day to the next, it's a completely mixed bag. How do you plan a system? How do you operate a system with such incredible variation? Well, I think we're driving on it. I think a lot of the answer sits underneath our seats of our Model S's and Roadsters and other cars that are available. We're part of a solution, though not the whole solution. Within an hour, these cars can, in theory, do something which is technically called reserves. We may not be doing anything. We've told the grid operator, or some aggregator has told the grid operator, my car is available. I'm currently charging at 30 amps, but you can ramp me down to 20 amps, or you can ramp me up to 40 amps. And in doing that, which could theoretically happen in real time, you can exactly countervail different patterns in wind. Now, when power plants provide that service, which they do now, they get paid for it. So the question is, how do we write the rules of the road so that the money saved by not paying generators comes to us to make it worthwhile for us to be offering our battery and the potential inconvenience of synchronizing our charging patterns with the requirements of the grid? Well, we got to do that. That's a tough tariff change to do, but technically we can do it. Intraday is a little harder because we've got to be able to coordinate our charging schedule with when power is expected. And that will require, well, again, we already have it. We have a computer in our car that's already synchronized to the grid. It can, through our wireless connection, we can tell our car when we plug in at night, I need to have this car full at 7 o'clock in the morning. And let the grid operator decide when that charging is happening. And that lets him, or lets the grid operator, shift the load from 1 hour to the next and help smooth those. If we actually think about a true vehicle to grid, we could then use the storage in the car to take megawatt hours from our collective cars out of the battery and onto the grid if the prices are high enough to justify that. Again, this is all, should be simple. You should be able to buy low and sell high and make money, or buy power during the cheapest time and save money. The trouble is almost all of the retail tariffs shield customers from that. There's a very defensive point of view that retailers, that they have, that we shouldn't be seeing the real price. That's somehow too hard. Well, if we saw the real price, we'd have the right incentives to do the right things and use our cars to help integrate more renewables on the system, make the grid more reliable, and let more renewables come on. So with that, Tom?
Thank you. So I'll just get right into it. 1997, Professor Willett Kempton, University of Delaware, published a paper in Transportation Research, and the quote is, "The potential resource of electric vehicle batteries exceeds all current electric generation by many times, that the value is not in bulk power but in responding when needed, and that the driver sets limits based on driving need within which the grid operator dispatches based on time of electric system need." That was a concept of vehicle to grid as he described it. It's still the concept today. AC Propulsion in '99 developed a Gen 2 drive system that had bidirectional power. So it could charge just like a normal EV, AC from the grid to DC for the battery. It could also take DC from the battery, create 60 hertz AC, and send it out onto the grid. Many power converters can do this. Very few of them are installed on cars today, but this demonstrated how it could be done relatively cheaply and effectively. And so AC propulsion drive systems still today are one of the few drive systems that are bidirectional in nature. There are also increasingly bidirectional off-board DC chargers that can work. And some of the Nissan cars have a bidirectional off-board charger that allows them to have power back and forth between the car and the home. V2G is ancillary services, at least as it's initially conceived, is ancillary services, not energy arbitrage. You're not buying bulk energy at night and selling it in the day, although you could do that. But as Robert said, the rates really don't allow that or encourage that. It takes a very high rate difference to make that functional, and it also creates quite a bit of extra wear out on the battery. What we're talking about is ancillary services where the grid operator, and every grid throughout the country has an operator who keeps things in balance, supply and demand, buys ancillary services. And ancillary services are simply the ability to add power into the grid or take power off the grid on demand in very short time intervals and in fairly small increments. So this is how vehicles could supply ancillary services. An aggregator would take many vehicles and present them as a whole to the grid operator, and various communication schemes, including input from the driver, would allow the vehicle to be optimized as part of this aggregate resource on the grid. Why would a guy want to have his car doing this? And the reason is that there's money in it. Ancillary service is a big market. It's a well-established market. It already exists today. And you can earn money by allowing a battery to be used for these purposes. So there's money to be made, and part of that money would go to other entities and part of it would go to the vehicle driver. And a big discussion now, and I don't want to get into it too much, but the simple idea is you get a check every month for being part of this. But the more likely outcome is that in the end you're able to buy an EV or lease an EV or lease an EV battery, some way of transacting where your cost of operation in terms of battery and battery wear out is reduced compared to a situation where you don't participate. So in a lot of work with the University of Delaware, and in 2007 at FERC in Washington, D.C., Professor Kempton and I drove this e-box from Delaware down to Washington, D.C., plugged it in right in front of the FERC building, had a live feed of the grid signal from PJM headquarters in New Jersey, and responded to these signals and had the first live real-time demonstration of a vehicle to grid, where the vehicle is actually responding to the commands of the grid that were also going out to all the other ancillary service providers. Now, I don't know if it was a coincidence or what, but Darmid O'Donnell, the guy this morning from Tesla, showed up at that demonstration. So I don't think any of this has escaped Tesla, and I'm sure they're looking at it as well, as he said. In the 5 years since, BMW has contributed 30 Mini-E's equipped with the AC propulsion drive system, and those 30 cars are now participating in a larger scale V2G demonstration on campus and in the area surrounding University of Delaware. The demonstration is called Grid on Wheels, and just this year, PJM, the grid operator, actually certified it as a bona fide supplier of ancillary services and able to participate in the market. And these cars have been doing that at a capacity of about 100 kilowatts, which is the minimum increment. And on average, when everything's working well and the cars are participating, each car earns about $5 a day for participation in this market. The group includes the University of Delaware, PJM, NRG, which is a big energy provider and has formed a joint venture with the University of Delaware to explore V2G possibilities. BMW, who contributed the cars, EV Grid, and recently Honda joined in with one car of their own. So they're starting to get a flavor and just to dip their toe in a bit to understand what this is all about. And the DoD is doing a completely separate program. They want to use V2G to insulate their bases or to help insulate their bases and allow them to isolate from the main grid in an emergency situation. So their first installation is the LA Air Force Base, but they have many more planned where they'll have a whole fleet of non-tactical vehicles on base capable of V2G. And finally, last year at an energy conference, Chris Shelton, who heads up AES Energy, they supply giant battery-based energy storage on a grid scale to various entities and use them for various different purposes. And so his business, he buys megawatt hours of batteries and puts them in giant containers with big inverters and sells them on the grid. And he recently bought a Tesla, and he said the dollars per kilowatt hour for that whole car is cheaper than he pays for one of these giant megawatt hour installations. And the car has everything you need except the bidirectional functionality, which is not that hard to include. Same applies to the Nissan Leaf. And when you look at the energy cost of the car as a whole and see that the actual battery cost is quite a bit less than the car as a whole, you can see that there's a lot of potential for using car-based batteries economically to supply the energy storage needs on the grid. That's about all I have time for, so I guess we have time for some questions, I hope.
All right, so we're going to pull the panelists up here, and we'll have time for questions.
Just a quick question. The top, should that be 85 kilowatt hours or 60? I don't think there are any 65s.
Probably whatever the right number is. I think it was based on 60.
You said that almost no one had retail people had the price incentives to sell high and buy low. There is time of use tariffs. I'm interested, how many people in this room are on a time of use tariff? So maybe it's not that impossible.
Yeah, and I think that there's a difference between time of use and real time.
Right.
Time of use is characterizing hours. But the fact is that, as we saw on the slides, it may be that the middle of the day, which is when PG&E is charging you the most, is actually the time when there is the most surplus power on the grid. So, the tariffs structures are dumb. And we need to use the fact that there's real-time information. Right now, there's a different price than there was 2 minutes ago on the grid. And that information is not passed down to you. So we can't actually help the grid as much as we should.
But that information is way down in that fluctuations are down at these wholesale prices around 3 or 4 cents a kilowatt hour, right? They're not anywhere near as high as the retail prices.
Right, and that leads a whole other discussion. But it would be nice to see that transparency so we actually knew what the value of power was at any one time.
Really good panel. Does this format of the EV battery to storage, it seems to me it would make a lot of sense from like a co-op standpoint when you look at groups of EV owners or groups of people that have essentially their own battery backup or could aggregate both from a negotiation standpoint and from a redundancy backup or size backup, that would be a natural offshoot or a way to organize this. Does that make any sense, or has that been part of any of the discussions?
Yes, it does make sense, and as UDEL and other proposed demonstration programs start up, they're looking primarily at using fleets as demonstration platforms for V2G, because the aggregation becomes very complex unless you have very large number, well, it's complex no matter what, but until you have very large numbers of individuals, it's difficult to be sure that you'll be able to provide the service that you promise or that you want to promise. But with a fleet, you have much more predictability, so you can get a fairly large number of vehicles that always come back to the same point or a known point at a certain time of day. So we're looking very closely at which fleets would make sense, and frankly, I mentioned earlier in my other talk that the U.S. Postal Service would be an ideal fleet if they can get organized, and a lot of people are looking at school bus fleets as well because they have large batteries and are available fairly regularly for a large amount of time during the day.
To expand on that, we're also seeing the evolution of what we call microgrids. So instead of everyone thinking about being part of the PG&E system, we might see a large university campus being ring-fenced with a connection out to PG&E, in which case it's a lot easier to sort of capture those internal synergies of the university vehicles offsetting or integrating with the solar panels on top of the gym and so forth. So I think these microgrids are going to force the utilities to accept better business models.
I'm going to be greedy and ask a quick question. There are two different ways, or two different levels, I guess, of the vehicles contributing. One being vehicle to grid, where the battery can actually discharge and provide power and generation. The other one being demand-based load, where you can tell the car, I need to be full by X amount of time, but you can choose when or at what level to discharge. What kind of studies have been done, if any, to determine the relative usefulness of starting with demand load and then going from there to vehicle to grid, whereas vehicle to grid might take technology that's not baked into vehicles today?
So first, I like to call them both vehicle to grid. Though one of it I call unidirectional vehicle to grid, and there's sort of a holy war over semantics, what it should be called. But it is a good question, and I did some of my PhD dissertation work where we actually looked specifically at unidirectional vehicle to grid of doing sort of just that demand response and how much money you could make versus if you can add just the bidirectional and add energy into the mix. And so you can make about 10 times more money if you can do bidirectional power flow, but with it comes the additional risk of you have to, unless the manufacturer gets on board and puts a bidirectional inverter into it, you're going to have to put aftermarket hardware and you risk voiding the battery warranty. So then the aggregator, for the additional money, has to assume the risk of warrantying the battery and the drivetrain and things like that. So there's sort of a give and take, and you currently don't. You see demonstration projects of both, but there isn't really anybody commercially just doing this on a regular basis. So the market still remains to be seen who's going to win out in the near term, because it hasn't happened.
And I think a key thing of starting small is we can begin to overcome the institutional resistance of regulators and the utilities to the idea that this is actually a reliable source of grid integration. And that institutional resistance is far bigger than the mechanical problems of wiring it up.
Yeah, and there's a lot to be said for unidirectional or V1G in terms of breaking down some barriers, but it's also a bit of a risk because if the standards that are being discussed relating to communications and vehicle hardware are not written so as to include V2G, then we're setting ourselves back until we can get everything back in order.
You've talked about, well, so the current demonstrations are being done in sort of a centralized manner, the 30 cars that are all together, and certainly it would be a lot more work to get to the point where a whole city of houses, EVs at a whole city of houses could be coordinated. But there's both the load balancing problem and also the problems at the distribution level. Do you think that this could get all the way to the coordination of houses in an amount of time that solves the distribution problem, or is the distribution problem going to have to be solved by just putting in overcapacity?
I think that's really a key question. It really expands V2G into the whole host of how the grid will be operated in the future and optimized to work with what I hope will be, huge numbers of EVs. And I believe that it shouldn't be that difficult to solve the problem for EVs to solve the problem that they themselves create, which includes both primarily distribution problems. And an example is a project we're working on where we're installing a stationary battery as a backup for a fast charger. And you can see that they want to cut down the peak on the fast charger to reduce their demand charges. But in the bigger picture, you're likely to have fast chargers and regular chargers all in the same area. And so it would be relatively easy, if you had that, to say, well, we don't need a stationary battery. When somebody wants to come in and have a fast charge, we draw power from the surrounding regular EVs that are plugged in at the same time if they are willing to allow that. And so in that sense, the EVs can solve their own problems, and they can also solve distribution problems by the same level of communications that allows, you need a lot more information, and that's what Steve Jurvetson was talking about. But with that information, you can allow not just EV loads, but all other loads to be coordinated so that the distribution problems and asset investment deferral can occur.
All right.
A final sort of wrap-up thought, and then we do need to go. You look at these devices sitting in our pockets, and Alexander Graham Bell would have no idea what this is or how it worked or why it worked. The power system today is fundamentally the same one that Edison and Westinghouse designed. You got big power plants, thick wires, thin wires, and stupid consumers. And what's challenging the industry is we are rebuilding that from the bottom up, literally from the bottom up, where the consumers are now generators, consumers are smart, they're wired, they're interconnected. And frankly, it's a whole wild world out there. It's a great time to be innovating, and there's a lot to be done. So thanks for your help on that, and thanks for all the vehicles you've got to help be part of the solution.
Yep, let's give our panelists a hand.